So we're going to be talking about galvanic cells or voltaic cells here and electrolytic cells. These are batteries. They're just fancy words for batteries. Okay. So we're going to talk about how batteries work today. And what we're doing is we're going to end up bringing in ideas or concepts from those redox reactions that we did back in unit, can't remember what it was, 3 or 4, whichever unit that's in. I think it's 4. Okay. So electrical energy, electricity, can be generated from chemical reactions. And it's these redox or oxidation reduction reactions where that occurs. So we've got electrons that are going to be transferred from one, they call it species, but from one metal or one item, they're going to get transferred, and they're going to get transferred to another metal here. Okay, so in this example, they've got silver and they've got gold, and the electrons are going across there. And I'm gonna show you today how you figure out which one's which, and how you know where the electrons are traveling. Okay, from which side to which side. So we're gonna learn all of that today. And this is essentially how your batteries work. Okay. When you have a battery, like one of the batteries like you would have at a TV remote or that sort of thing, when you have one of those batteries, you've got one side here, and then you've got another metal over here. You probably heard of like lithium batteries. Well, one of those metals is lithium. Okay. And the electrons are going to move across that. And typically in your batteries, they have what's called a porous divider, where these charges can move back and forth. And we're going to talk about why those charges need to move back and forth here in a few minutes. But we've got these electrons traveling from one side to the other. And when they travel like that, that generates a current. That's your electricity. So this is one of those cells. In a standard cell, that means that you're 1 molar, and it's at 1 atm for your pressure, and your temp is 298. Okay, this is called a half cell, and this is the other half cell, and then they're connected. The solids are placed then in a solution where they have, and they're called the electrodes. So you've got an electrode here and electrode here. The oxidation is the anode, and the reduction is your cathode. So the way that we remember that is red, cat, and an ox. So your car battery, have you ever looked at your car battery? There's always a red terminal on there. They have it marked with red.
Yes, with the jumper cables.
Yep. That's where the cathode is. That's where the reduction is happening in that car battery. That's why they label it. That's why it's colored red.
If you put them on the same colors or on different colors, will your car explode?
I don't know for sure, but bad things happen. That's what I do know.
I have a question. What happens when you fill up your car with gas but don't turn it off? What happens then?
It could cause a spark and you could go boom.
Wait.
What happens if you put diesel in your car?
It just burns out the engine, right?
Yeah.
The diesel will burn your engine out. Yeah.
So you need to get a whole new engine?
No, they go in through and they flush it. They have to do a whole flush. It's like $300-400 to get it. My husband had a friend that had that happen. So yeah, don't put diesel in your car if it doesn't take diesel.
Well, I was trying to do it one time, and I was really frustrated because the diesel pump would not fit into my car, and I was like trying to jam it in there. I was like, God, it's not working. And I realized I had the wrong pump in there, and I was like, this just saved my life.
Yeah.
All
right. So you've got your anode. This in your car battery is always black. This is going to be red. This is where your reduction happens. This is where your oxidation happens. So this is black in your car battery. This is red, and because it's red because that's where the reduction is happening. Okay, and then the other one's the oxidation. So the electrons are going to flow through the wire. When the electrons flow through the wire, this is actually going to form more gold on that electrodes. So this is going to get bigger and this will get smaller. Okay. So hang with me. I'll explain it to you as we go through. I'm just kind of setting it up now. Okay. All right. So we've got these electrons flowing, and then we've got something called a salt bridge here that's going to help to keep the charges balanced on each side. Okay. So, like I said, that salt bridge, or it's a porous disc, but you've got those in your car batteries as well, and they're going to balance those sides out. To predict which of the potential reactions is thermodynamically favorable, you have to look at a standard reduction potential chart, and they would give one of these to you on the exam. I have provided one for you a couple pages in. It looks like this. Okay. So when we look for those reduction potentials here, for gold, it's 1.5. For silver, it's 0.8. Okay. So the one with the higher value needs to get reduced. So if you look at these two numbers, this number is bigger, so we need to reduce this number. That's how I remember it. Okay, so that's where reduction is going to be. Yeah.
Okay, so are you just using silver and gold as an example? Like, can other metals?
Oh, it's other metals. Oh, yeah. Yeah. So we're going to, in a minute, we're going to do one between magnesium and sodium. Okay. Yeah, you're not going to have batteries typically that have gold in them. It's just too expensive. Okay. But they're just using these as examples here. Okay. So the way I remember that reduction is going to take place here is that if you always want to reduce the bigger one. You want to make it smaller. So that's how I remember reduction. Does that make sense? Okay. So which number is bigger? This one. This is reduction. Okay. So we're going to predict which one's thermodynamically favorable and which one would be thermodynamically unfavorable. And the one that ends up being the bigger number is going to be the reduction, and then the oxidation is the other one. Okay. So then you subtract these two from each other. Well, this one's got to get flipped, and then you add them together. Okay. So let's go through this one. We have gold and we have silver. So I'm going to go through this one with you on a separate sheet of paper here. I don't know if you want to flip to that reduction potential page or take out another sheet of paper, and we can go through this step by step and talk about it. All right, so I have this set up here. I don't want to put my arrows on here yet because I don't know that this is the way my arrows are going to go. So I'm just going to get rid of those right now. All right, I like to put my anode on this side. Okay, so when we're doing these, we need to look at the reactions that are taking place. For this one, we had our two reactions that they gave us was Au 3 plus 3 electrons yields Au, and they told us that that was 1.50. Then we had silver. And that is going to be 0.8. Okay. Now, which one of these is bigger? AU. So this is where my reduction is going to take place. This is where my oxidation takes place. Now, let's talk about oxidation and reduction. Which one? Okay, remember oil rig? Oxidation is loss and reduction is gain. At this point, the way these are set up, they're both set up as which ones?
Oxidation.
Reduction. They're gaining electrons.
Oh,
Okay. So these are set up as reduction, but this one needs to be set up as oxidation. We already figured that out by looking and seeing. Okay, yep, we got to flip it. So I'm going to flip this guy. I'm going to have Ag here. It's going to give off an electron plus, making Ag plus. But if I do that, I need to flip the sign
negative
on this one. Okay? Everybody cool with that? All right. Like I said, I like to keep my anodes. I don't know why. It's just the way I learned to do it. I like to keep my anodes on this side. It doesn't matter which side it's on. And on the test, sometimes you'll even see them flipped around. So you got to pay attention to it, okay? But I like to put my anode over here. So I'm going to call this one my anode. I'm going to call this one my cathode. The cathode. Yep, because it's fat, cat. The cat's getting fatter. And then it's a red cat too. It's a red fat cat. It's reducing. Yep, this is where your reduction is taking place on your cathode. So that means that I'm going to have gold over here. So this right here is going to be gold. And they're going to be 3 plus. No, that's just gold. Hold on. Don't right down there. That's just gold. Yep. So this is gold. Yep, I'm going to get to that. Just don't get ahead of me. Okay, so this is where the reduction is taking place. Okay, my anode then is an ox. Okay, so this is where my oxidation is taking place, and we determined that that's taking place with silver. Okay, everybody cool with that? Okay, so then inside here, I'm going to have some sort of electrolyte in here that consists of silver. And why don't we just do, it doesn't look like you did anything in your diagram for that. So we're going to call that, oh no, they did have nitrate in there, didn't they? They did have nitrate in there. So this is AgNO3 here, but these are floating around as ions. Okay, and over here we've got AU3 plus and nitrate floating around. So this is another Okay, so that's floating around in there. Does that make sense? Those are aqueous ions of AgAuNO3, aqueous ions of AgNO3. Okay. This is called a salt bridge. And what they had in their salt bridge was they had, can you guys please not? They had potassium and they had nitrate in that salt bridge. Okay. Now, this is how the battery is going to operate. Okay. What's going to happen is one of these AGs here is going to move out. Why are you not moving? Come on, move out for me. There we go. It's going to move out into this solution. Okay. And when it moves out, it's going to give off an electron. So that Ag is giving off an electron. That electron then is going to go up into the wire, and this is going to become a plus. So this just happened there. Does that make sense?
Is there a reason why it gives off electrons?
Because when they're connected like this, it's thermodynamically favorable for this redox reaction to occur because it gives free energy. Okay, so that's going to move out. It's going to give off an electron, become positively charged. That electron then is going to move over to here. So that electron travels over to here. Okay, and then another one of these is going to happen. So another one of these is going to go off into, actually 3 of them total. So I'm going to put this one back, I guess. Shouldn't go back, will you? So 3 of these are going to come off. These are all linked together, so I'm just going to grab them. I'm going to get 3 electrons traveling across here. Okay. So I've got these 3 electrons traveling across. 1, 2, 3. They're going to travel over to here. They're going to hook up with one of these guys. Okay. He's going to grab one of these. Oh, they're all written together. Darn it. I'm just going to sneak another one on there. So he's going to grab that guy, bring him here. Those 3 electrons there are going to hook up with this, and that's going to become gold. So it grabbed one of these ions here, brought it here, hooked it up with those 3 electrons, and it made gold on here. And that's why this one's going to get bigger. So over time, this guy will get bigger because it's putting gold on there from the solution with the electrons. And this guy is going to get smaller because those ions are going to go out into here. Now, the problem is that we start to get a charge imbalance here. So I've taken something here that was a +3, okay? And by doing that, now this has become more negative, this solution. So what has to happen is I've got to get 3 of these Ks to move down into here from the salt bridge to make up for the 3 charge on this guy that I just brought in. Yes?
What does this all do?
It's going to help neutralize the change in charges. So because I took a 3+ away from here, okay, this was neutral. If I take a AU3+, this becomes more negative. So I need to bring in 3 Ks from the salt bridge to balance out that charge difference. Okay. Over here, I made this more positive by 3 because I added 3 positives in here. So I need to neutralize those 3 positives by bringing in NO3 minus. If I bring 3 of those in, it's going to neutralize those 3 that I just brought. Good? That making sense? Okay. And that's how your batteries work.
Very confusing battery.
That's why we're going to spend some time on it. Okay. This isn't my last, like, what I'm going to explain to you. I went through and explained that one. Now we're going to do another one, which is the I do, but I actually do more than what they gave you room in here for you. We're going to do it in this. We're going to do it with one of these images here. There. Okay. So we're going to set this up and we're going to do this I do. All right, you ready? So the I do here, they are giving us sodium and they're giving us magnesium. Okay. So we have Na. Which one of those is more positive?
Mg plus 2E.
Okay, so that's where my magnesium is more positive. So my magnesium is going to be my reduction. So this needs to get reduced. And by reducing that, that means that we are going to reduction is gain. So it's going to be gaining. So Mg2 plus 2 electrons makes Mg. That means that this is going to be my oxidation, and my amount for Mg is, magnesium is negative 2.37. Okay. And that means that my sodium then is going to be oxidized, and oxidation is loss. So it's going to lose to an electron, but we need to lose 2, right? And we flip this around, so we've got to flip our sign, 2.71. Okay.
Why did we turn it into 2 Na?
Because this needs to gain 2 electrons.
Okay, so you put 2 in front of.
Yep. Now, that does not change this number, though. The only thing that you change on these numbers is flipping the signs sometimes.
Okay.
How do you find out which one?
So I looked at the numbers. I had negative 2.71 and I had negative 2.37. Which number is more positive? Which number is bigger?
2.37.
This is where my reduction is. And this is my oxidation. The higher number is the reduction. Reduction is gain. So this has to be gaining electrons. Oxidation is loss. That means that this has to lose electrons. Good. So they give you these reduction potentials when they gave us the equations. They gave them to us both as reductions. So we needed to flip this around to make it oxidation.
What is it that last time was that?
This is the voltage that it creates as during that reduction potential reaction. And if you want to know the overall amount, then you add these values together. So when we add these together, our overall voltage is going to be 0.34.
What do you think I?
So that's a voltage, 0.34.
Yep. All right. So now, again, I always set this up as my anode, set this up as my cathode. I can't guarantee that it's always going to be set up that way. It's not a standard amongst chemists. It's just the way I tend to do it. That way my brain is always thinking about it the same way. Because there's a lot going on here, right? Okay. So we need to set up a salt bridge. They didn't tell us in our problem what our salt bridge is. I'm kind of modifying a little bit this I do, we do thing. So we've done A, B, and C and D here. We didn't do the overall equation. I guess we could do the overall equation too. So letter A asks for the overall equation. So that would be 2Na plus Mg2 plus yields Mg plus 2Na plus. That's your overall reaction. So there's your overall reaction. That was the answer to letter A on the I do problem. They asked for the calculation for the voltage. So this is the calculation for the voltage. This is letter B on your I do problem. They asked for the anode. Which one takes place at the anode, oxidation or reduction? Oxidation. It's an-ox. They're both vowels, if you need to remember it that way. Okay, so this is the reaction that's going to take place. So this is letter C on the I do problem. And then that means that this reduction is red cat, a fat red cat. This is letter D on your sheet. Okay?
Does adding the coefficients change the voltage?
No, no. This is considered to be an intensive property. So if you remember back to your first year chemistry where we talked about extensive and intensive properties of matter, intensive doesn't matter how many you have. That's irrelevant. This is not going to change. So this is an intensive property. We're not going to alter that based on what we multiply this by. Okay? That is hard. It is really hard because almost every time that I've ever made you multiply through by a coefficient, I've made you multiply the next number by that coefficient. And so this is where you've got to kind of retrain your brain and just go fight the urge, fight the urge. I have to do that every year. I have to fight it. Yeah.
So what does it mean if the half reaction takes place at something?
Right. So they're asking you which one of these is going to be the anode and which one is going to be the cathode. Okay. Each one of these is called a half cell. This is half a cell. This is a half cell. And the way you determine which one is going to take place where is that you remember the acronym red cat and an-ox. So oxidation is going to take place at your anode. And your cathode is going to be your reduction. All right, so let's talk about how this is going to happen. We know that our anode is going to have sodium. So this is going to be sodium metal here. This is going to be magnesium metal. Okay. In here, I'm going to have a solution. They didn't tell us what it was. Let's just use NO3. Oops, that shouldn't be a plus. It should be a minus. So nitrate again. Let's just use nitrate. And let's use sodium. It has to be the same metal ion that exists in this metal. Although I don't know that that necessarily matters. Yeah, anyway, it typically is. Okay, so this is Mg2 plus over here, and this has to be the same one. I know that for sure. Yep, same ion as this metal, because that's going to become part of that metal. And then you've got some other anion over here. We'll just do nitrate again.
Is it always nitrate?
No.
What can you use?
You could use chlorides. You could use any kind of, yeah, it doesn't matter.
If we choose the elements for like salt,
It just needs to be something that's soluble in water, or typically soluble, like one of your snaps. And they'll tell you probably what it is. You know, the salt bridge contains this. And then I'm just going to throw nitrate in there too, because that's always soluble. Okay. All right. So let's see how this battery is going to operate now. We said that this is going to be our oxidation. So what's going to happen is one of these sodiums, or actually let's take two of these sodiums, are going to come off of here. They're going to become positively charged, and they're going to give off electrons to go over here. Our voltmeter would read what? 0.34 volts. Our electrons are going to move over to here. One of the magnesiums from this solution is going to grab a hold of those two electrons, and this is going to form magnesium here. Wake up, Jade. Now, in doing all of that, we have an imbalance of charge. So I have added a positive charge into this solution. Which one of these things do I need to go in to balance that positive charge out here? NO3 minus. Yep, I know it's not in the greatest of shape there. So I'm going to add an NO3 minus over to here. So this is going to come down this way. And then I'm going to have to add two potassiums into here to balance out that Mg2 plus that was grabbed a hold of here.
Okay, so when you say that you have to but does it just naturally?
It just naturally happens, yeah. Yep. Yeah. So, guys, shh. The Mg from here went from here into here. So I lost two positive charges here when it went into this metal. So I need to replace those two positives that came out of here. I need to replace that with two positive charges. So I needed two Ks to come down into here. Yes? Okay. All right, so that's how those work. Which one of these is going to be gaining mass? The cathode. This is my fat cat. It's grabbing a hold of the Mg. It's grabbing a hold of the electrons, and this is going to get bigger. This will then get smaller. That's why they call it a fat red cat, because this is getting fatter. This right here is going to get fatter. Okay, good.
Your baby. Your baby.
Oops, that's the wrong side. All right, so let's look at this reaction here. Write a thermodynamically favored, balanced overall reaction.
Sophie, did we write the half reaction, or are we doing that later?
She was like, no.
Okay.
I did the half reaction on this other one. Yeah, I did those.
Yeah. In the beginning.
Here. You talking about these two?
Okay.
This was C and this was D.
Okay.
That's why I wrote C and D next to it as I was going through it. But you guys kind of have your own little thing going on over there, so sometimes you miss stuff.
Okay.
Good?
I don't know if you're right.
Huh?
Well, what's E and F then? Is it the anode was
I'm
draw?
trying to put this on.
So
Oh,
E asks which one, after the reaction has been allowed to take place, what will happen to the anode? And that's what I was talking about. This is going to lose mass, and this will gain mass. So that's F. The cathode gains mass. The anode is going to lose.
Go back to the C.
Yeah. Well, there's the process of when we should.
whoa.
All right, so we need to write a thermodynamically favorable reaction here. Which one of these is going to be my my reduction, and which one's going to be my oxidation?
Oxidation.
Reduction's the top. FE.
Reduction's the top one because that number is more positive than this number. Okay, this is where my oxidation is going to take place. So what I need to do is I need to take this reaction here. Oxidation is loss. No, oxidation is loss. So I've got this guy written. He's losing. Reduction is gain. This is loss. So I need to flip this reaction around. So this is going to become Fe yields. Maybe that's what I'll do is just go Fe yields. And then I will get rid of this stuff. Then I'll have to rewrite as much stuff. And then what do I need to do to this sign here? Yep, I need to make this positive now. Okay. So write a thermodynamically favored balanced overall reaction. So if I want to write a reaction here that's balanced, that means my electrons are balanced. So I'm okay. I don't need to modify these amounts at all. This is going to become 2H3O plus Fe yields Fe 2 plus H2 plus H2O.
Wait, question.
Yes.
So It's about the silver and gold one. So when silver is being rewritten as an oxidation reaction, why does it happen with blue?
Because we had to get this, it needed to balance out. We had 3 electrons here, so we had to generate 3 electrons here to make that happen.
And then just distribute that for everything.
All right, we're on to this guy. So calculate the voltage. All we have to do is add these up. So this is 0.45 volts. Write the half reaction that takes place at the anode. Half reaction at the anode is oxidation. So this is going to be my letter C here. Okay. And then write the one that takes place at the cathode. That is going to be my letter D. After the reaction has taken place, what happened to the anode?
It lost.
Lose mass.
It lost.
Right, it's going to lose mass. And the cathode will
Gain mass.
gain
So
mass.
it'll always be anode loses, cathode
Yep.
gains. Okay.
That's why it's a fat cat. The cat gets fat. This isn't balanced. Oh.
We would need a 2 instead of the H2O, right? Or is that just?
What did you just say?
That's never done.
No.
You said,
No, I didn't.
you said
No.
bark.
Yeah, I'm not sure.
No,
Yes, but it's a female dog.
no, but not.
Typically, those are given to you.
I'm
So
done. I can't
I
even.
wouldn't worry about it. Okay. So tonight, I want you to try to do these, and we're going to talk about batteries some more tomorrow, okay?
And if you balance out the equation, you don't have to multiply it by
That's the hard part to keep straight, because you have this compulsion that you want to do that. Because, like, we've done that with everything all the way up until today. And now all of a sudden I'm like, nope, don't do it.
So like, if we have to balance this out, we don't have to do it.
Oh,
Do today.
I probably would never done this before, so.
I'll do it.
She's up to 5.
Yeah, yeah. And then when you're doing it.
Whoops.
Whoa. I'm just gonna wait till you finish and I'm gonna check.